Teacher down here. Looking at my stump. Uh, nice stump. If you look in the background there, you can see the mountain. That's our view. That's a gorgeous view. Sun's coming up. It's a balmy 50 degrees here. Very comfortable. So, Teacher Dan wants to talk about mathematics. Now, math, see, y'all probably think I'm some kind of hick, after everything, the way I talk and everything. But I'm really not a hick. I happen to be, a physicist, which means I studied a lot of mathematics. And when I teach math, I tell my students, and there is an educational point in here, really. My students have been taught, that PEMDAS, or the order of operations. That's the rules. That's what they've been taught. They've been taught that you got to follow those rules. And I always, at some point during the year, we get into the properties of real numbers, and I say, you don't have to follow the rules. You don't have to follow PEMDAS, I should say. You have to follow the laws of numbers. And these laws of numbers are actually not that many or that difficult. And I just thought it'd be kind of cool to lay them out here so that those of y'all who went to school and, when you took algebra and maybe calculus and everything, you thought, that the order of operations was like the law of the land, and it ain't. The law of the land is the properties of real numbers. So there's additive identity, which is when you add 0 to a number, you get the same number back. There's multiplicative identity, which is when you multiply a number by 1, you get the same number back. The identity properties are super important because they're the basis of all the other stuff we do in, math. So then there's the inverse operations, which is additive inverses. You add a number to the negative, a counterpart of that number. So, a plus negative a, that equals 0. So you can make zeros. That's nice. It can make things go away. And then there's multiplicative identity, or inverse, which is where you multiply a number by its reciprocal. So a times 1 over a equals 1. So you can make ones and zeros, and everything comes back to that fundamentally when you're dealing with numbers. You have identity operations and the inverse operations, and then you have associative properties where you can do multiplication and addition, and you can rearrange things using grouping symbols like parentheses. As long as you're adding and multiplying, you can do that all you like. Then there's the commutative properties of multiplication and addition, and these are pretty much the ones you need, to do algebra and to do calculus. So when I explain to my students, when we were kids, when I was a kid and older people were kids, we learned all about long division and multiplication and everything, and it's taught to you like it's a separate thing, but it's not. Right? Division is simply multiplication by reciprocal, and subtraction is addition of a negative. And so there are really two operators in mathematics. One is addition, one's multiplication, and you can express everything in these terms. And to go even deeper, you can express all geometric concepts in algebraic terms and vice versa. So when you get to calculus, it becomes this really nice kind of marriage of geometry and algebra. And the reason people hate it is because algebra always was some kind of a struggle, and it was for me too for a while. You know, algebra for me when I was a beginner was hard, and I didn't really fully get math until, I'll be honest, I took a lot of math in high school and college. I did calculus for a long time and differential equations and so on. But it wasn't until I was a junior in college when I realized uh, how it all clicked. You know, I took a course in uh, non Euclidean geometry, which ended up being very interesting. And I used a lot of calculus in my explanations, which I think drove my professor nuts. But uh, it was a course for math majors, right? I wasn't a major in math. I was a major in chemistry, and I took this course because I was in a program to become a teacher of math and science. And so I'm in this course with a bunch of math majors, and I'm thinking about things maybe a little different from the way they were. And the professor had this format for this course where we kept like a journal, and in the journal we worked our problems and explained our responses, our answers to the problem. And this guy had a definition of the word proof that has stuck with me throughout the years ever since. And back in high school geometry, and when you're doing even sometimes in calculus, you do these like kind of 2-column proof things, and they're fine, they're great. You put a premise out there, you put an idea out there, and you give a postulate or a theorem that proves that step is correct. And as long as your steps are all right, your proof is correct, right? But David Henderson had a different concept, I think, of the idea of what a proof is. And he said a proof is an argument that would convince a reasonable skeptic. And that stuck with me because reasonable skeptic is somebody who can be convinced by evidence. So an argument that would convince a reasonable skeptic is a pretty good proof. And so it's more of an inductive concept of proof than the old deductive 2-column proof in geometry that you took in high school. It's different, and it stuck with me, and it's something that I use as a guiding kind of light in my thinking, because that's what I think a proof is. And so mathematics, very basic stuff, but it's not hard. I mean, you just learn the operations, learn the rules. You can do it. And so my 7th and 8th grade students want to argue with me. We were taught, well, PEMDAS, you got to do it. And I'm like, well, if you do it, I mean, it's kind of like those gutter rails at the bowling alley where, when you're a little kid bowling, it'll keep you from guttering the ball. But it's not the way numbers work. You have to be flexible once you get good, and you can violate PEMDAS lots of ways. Anyway, and still get the right answer. PEMDAS will keep you from screwing up, but you can get the right answer and not follow it if you understand how numbers work. Anyway, more to come on calculus, I think. There's a lot of really cool stuff there, and it really isn't that hard. It's a matter of mindset. So, Teacher Dan, signing off.